Annenberg Media.
Why is there summer in the United States and at the same time winter in Australia?
Why are the days longer in the summer than in the winter?
Why doesn't it snow in Haiti?
Throughout history, the sun has been central to the lives of all people. In cultures around the world, the sun has been both studied and worshipped. The ancient Chinese people believed that there were originally 10 suns, one appearing on each day of their 10-day-long week. The archer Yi shot 9 of them, leaving only one sun. The Norse people depicted the long winter months as the journey of Skirnir into the underworld. And in Hindu mythology, the sun god Surya was believed to heal the sick.
The Fon people in West Africa believed the sun god Liza brought them heat and strength.
And the Mayan architecture and calendars showed their observation and understanding of the movement of the sun and the effects it has from season to season.
Today we know that the sun is the star that is the energy source for the entire solar system of which our Earth is a part. The sun is a rotating ball of very hot gas. Nuclear fusion occurring deep inside the sun releases photons. At the sun's surface, light radiates out in all directions.
So why, if the whole Earth is receiving the sun's light energy, are regions of the Earth so different in temperature? Why is winter in New England different from winter in Panama or winter in Brazil? It's these questions we'll explore in today's workshop, Sun and Seasons. Welcome to Shedding Light on Science. I'm Christine Jones, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics.
And I'm Anita Greenwood, a science educator at the University of Massachusetts Lowell. Today we'll discuss how different parts of the Earth receive different amounts of light energy, which results in the Earth's seasons. In particular, we'll look at the tilt of the Earth's axis and how the hours of daylight change throughout the year, the absorption of light energy by the Earth and the transformation of light energy. And we'll also touch on the long-term history of climatic changes on Earth.
Our sun is a relatively constant star. The amount of light it produces has been observed to change very little. Although the primary emission from the sun is in the visible and infrared, the sun also emits low-energy radio photons and higher-energy ultraviolet and X-ray photons. Fortunately, the Earth's atmosphere prevents much of the high-energy photons from reaching us. But without infrared and visible light, our Earth would be a very cold and barren place. Photons from these regions of the electromagnetic spectrum heat the Earth's surface and its atmosphere.
We have evidence that light energy heats the Earth because objects feel hotter when they've been in the sunlight. We visited Lolita Darby's 5th grade class in Portland, Oregon, as they were doing just that, feeling the heat of the sun.
Okay, let's go. That's Jennifer.
Toes is pretty.
We've got the grass here, the wall here, blacktop there.
This is harder than us. This is hot. Since it's made out of tar, Shade is cold, and grass is hotter than shade.
And then this is warm. And this top part, this is hotter. This is hotter than this. And it seems like it'll be the same. It seems like it'll be the same because they're both the same thing as blood and wood.
The children discover that objects feel warmer if they have been in the sun, but are not equally warm. Light energy is absorbed or reflected by the various materials to different degrees. The children notice this as they feel the difference in temperature between the white lines on the tennis court and the black tar.
I think the white reflects heat. The white part. If you put your feet on black, right here. This is closer to black, so it makes heat come. This reflects it.
Look, this part right here. Shade, you know. When you put it in shade is very cool.
It's very cool, very cool.
And then on grass,
You guys are all playing football. Thank you very much. Thank you.
What happens to the light energy absorbed by objects? Let's think about light shining on this rock. When the rock absorbs light energy, it is transformed to internal energy. We measure this as an increase in the temperature of the rock. If the rock's temperature is higher than its surroundings, it'll radiate energy as infrared photons. If I hold my hand near the rock, I can detect these infrared photons as radiated heat. But this is not the only way that energy leaves the rock. If I touch the rock, some of the rock's energy flows as heat to my hand. This type of energy transfer is known as conduction. The rock also heats the air around it, primarily through conduction. Energy in the rock is transferred to the air. As the air is heated, it rises. The rising air transfers heat through a process known as convection. Convection is important in explaining many weather patterns. We'll talk about convection more in our next session, Wind and Weather.
When sunlight strikes our Earth, photons are absorbed, and this has a heating effect. We see this in the daily cycle of high and low temperatures. The Earth rotates on its axis once every 24 hours, producing the cycles of day and night. Temperatures usually fall at night and rise during the day. The coolest temperatures are often just before dawn. Then, as the sun rises, it heats the Earth. Daily high temperatures usually occur in the early afternoon. You may have wondered why it often gets cooler in late afternoon, even though the sun is still up. Think about a day at the beach. At midday, the sun is high in the sky, you feel hot, and you can get sunburned pretty quickly. But late in the afternoon, it feels cooler, and you're less likely to get sunburned. Let's join a group of children in Boston, Massachusetts, as they investigate the effect of sunlight striking the Earth.
The children use the flashlight to represent the sun, and the paper represents the surface of the Earth.
It would always be winter, and only we would get summer.
When they hold the flashlight straight above the paper, the flashlight makes a bright circle of light on the paper.
It's kind of like a spotlight.
Now, if they tilt the flashlight, what happens? The circle of light gets stretched out. The same amount of light is shining on the paper, but now it is being spread over more paper. We can model the sunlight shining on the Earth if we keep the flashlight stationary and tilt the paper. When the paper is tilted, it's like the late afternoon or the morning sun.
It's not hitting us directly like if the flashlight was like this. It's kind of like this, so it's still hitting us. Right. It's just not direct, so we don't feel the heat.
Then the world changes. So then now.
But when the paper is flat, it's like the intense midday sun.
Dark time right here is nighttime.
Now let's look at a model of the Earth. First, we placed a piece of screen on a slide to make a grid pattern. When we shine this on a flat surface, the squares all appear to be the same size. there is an equal amount of light energy in each square. Now let's shine this same grid pattern on a curved surface, a globe. Now the squares are not all the same size. Those in the center are smaller than those toward the poles, or those to the east or west. Since each square is still getting the same amount of light, where the squares appear larger, the light is more spread out. It's less intense. Anyone standing along a line drawn from pole to pole through the center would see a midday sun. This provides them with their most intense light of the day. But because the Earth is curved, sunlight in the morning or afternoon is less intense. So we can see that because the Earth is a sphere, that different regions will get different amounts of light. But this still doesn't explain why we have seasons.
In the northern hemisphere, the heating effect of photons on land and water is pretty obvious during the summer months of June, July, and August. Even Alaska warms up in the summer. But if the sun is shining all year round, why is summer always distinctly hotter than winter, except if you are living in the tropics? Let's explore how the amount of sunlight striking different parts of the Earth changes as the Earth revolves around the sun. We know that it takes a year for the Earth to orbit the sun. But as the Earth revolves around the sun, the Earth's axis is not perpendicular to the plane of the orbit. The Earth's axis is tilted at an angle of 23.5 degrees. Now let's return to our globe and again use the light grid. Remember, on a flat surface, all the squares are the same size, but on a curved surface, we can use the squares to see how the light is spread out. When the sun shines on the Earth in this position, it is winter in the northern hemisphere and summer in the southern hemisphere. Now let's move the Earth globe to the opposite side of the sun. Remember, this would take 6 months to do. And look at the grid of light squares again. The squares are now smaller in the northern hemisphere, so the sunlight there is more intense. It is summer. In the southern hemisphere, the squares are larger and the light is less intense. It's winter here. We can also use a light meter to measure the intensity of the light in each area. We can clearly see that the light is more intense in the areas of the globe where the grid lines are closest together. We can compare the intensity of light to the temperature with another model of the Earth.
In this demonstration, we covered a sphere with liquid crystal and outlined the continents in white. We know that when sunlight strikes our Earth, the absorbed photons heat the Earth. The liquid crystal on the surface of our globe will register this as a rise in temperature. When the North Pole is tilted away from the sun, the southern hemisphere receives the most intense light, and it's summer there, and winter in the northern hemisphere. The highest temperatures occur where the most intense light hits the Earth. Now let's tilt the Earth so that the northern hemisphere is tilted toward the light. This time, the northern hemisphere receives more intense light and the temperature rises. Cooler temperatures are measured as we move southwards. Let's think about this in terms of seasons. What season would the northern hemisphere experience if the Earth were in this position? Make your own model Earth with a piece of crumpled paper to represent the Earth. And use a pencil or a pen to represent the Earth's axis. Use any object that you can move your model around to represent the Sun. Use the model to show the Earth's positions when the northern hemisphere is experiencing each season. Draw this. Why does the southern hemisphere experience summer when the northern hemisphere is experiencing winter? In order to explain the seasons, not only do we have to know about the tilt of the Earth, but we also need to know about the shape of the Earth's orbit around the Sun. Many children hold the incorrect idea that the seasons are caused by a change in the distance from the Sun to the Earth. This idea commonly comes from perspective drawings that make the Earth's orbit around the Sun look highly elliptical. Think of it this way. If I draw this cup from the side, the top looks like an ellipse. Now, if I look down on the cup and draw it again, from this perspective, the top looks circular. The Earth's orbit around the Sun is almost circular, so distance cannot be the reason for the seasons.
The model of the Earth and the Sun that we've used today in our workshop is not to scale. The diameter of the Sun is more than 100 times the diameter of the Earth. 1,000,000 Earths could fit inside the Sun. In a realistic model, if we used a ball for the Sun that is 25 centimeters across, then the Earth's diameter would be only 1/4 of a centimeter. To get the distance scale right in this model, our quarter-centimeter Earth would be nearly 30 meters away from the sun.
Let's look again at our model to show the Earth's orbit around the sun. The model shows the Earth revolving around the sun. One revolution takes 365¼ days. During its orbit around the sun, a line through the Earth's axis points toward the same direction in space, toward Polaris, the pole star. As the Earth moves through this part of its orbit, the southern hemisphere is receiving more intense light, while the northern hemisphere receives less intense light. It is summer in the southern hemisphere and winter in the northern hemisphere. When the Earth moves through this part of the orbit, the northern hemisphere is receiving more intense light, while the southern hemisphere now receives less intense light. It is summer in the northern hemisphere and winter in the southern hemisphere. In between these seasons are autumn and spring. As the Earth travels around the sun, there are 2 times when the Earth's axis is not pointing either toward or away from the sun. If we were standing on the Earth's equator at these times, the midday sun would be directly overhead. These transition times are autumn and spring.
You may have wondered why the Earth's axis is tilted. In fact, most of the planets in our solar system, just like the Earth, rotate on axes that are tilted with respect to their orbital plane around the sun. We're not sure why this is so. Perhaps it is due to violent collisions common in the early solar system. We've talked about daily and seasonal changes, but within modern times, changes from the normal variations have been modest. As you watch your local weather, we seldom break record high or low temperatures. But over long time scales, the Earth's climate has not been constant. For most of the last 600 million years, the Earth was much warmer than it is today. There were no polar ice caps and no glaciers, not even on Mount Everest. However, beginning about 3 million years ago, there has been a series of cold periods known as ice ages, and intervening warm periods that are similar to our present climate. Jean-Louis Agassiz was the first to conclude that the northern hemisphere was once covered by glaciers.
Jean-Louis Agassiz was born in Switzerland, where he began his career in science. On a trip to the Swiss Alps, Agassiz noticed that a hut built on a glacier had moved a mile since he first saw it 12 years earlier. Later, Agassiz drove a line of stakes into the glacier and returned the next year to find the stakes had moved. This provided evidence that glaciers flow, gouging great valleys, carrying large boulders long distances, and leaving mounds of debris in their path. Agassiz realized that these signs of glaciation could be seen where no glaciers existed. This led him to formulate his theory that a great ice age had once gripped Europe. Agassiz gathered evidence for this theory all over Europe and in the United States. Glaciology is now primarily concerned with interpreting global weather in the past and predicting weather in the future.
A number of complex processes cause the changes in the Earth's climate. Possible causes include changes in the Earth itself, such as mountain building, variation in the tilt of the Earth's axis over time, or small changes in the Earth's orbit. And finally, perhaps changes in the sun's intensity. We visited the Harvard Museum of Natural History to learn about how these changes in climate affected the Earth's inhabitants.
I'm Elizabeth Hammond-Pyle, and I work in Harvard's Department of Earth and Planetary Sciences. There have been a number of ice ages throughout time. The most recent ice age occurred in the Pleistocene, and it's considered the modern ice age. So 20,000 years ago, much of North America and Europe was under glaciers. So there was a glacier that ran, it started in the Hudson Bay and it covered all of New England and much of the Midwest. There was also extensive glaciers that ran from the Canadian Rockies down into Washington, Idaho, and Montana. During the most recent ice age, much of the water was locked up in glaciers. So as a result, sea levels dropped. So continental shelves were exposed, and other parts of what's now underwater were also exposed. For example, the area between Alaska and Siberia, which is called the Bering Strait, was exposed as land. During the ice age, there was a lot of migration of species. Because the climate was changing very rapidly, species moved around a lot. Animals migrated across the Bering Strait because the land was exposed. One of the most well-known animals that migrated across the Bering Strait was probably the group of elephant families. These include mastodons and mammoths and a lot of their relatives. In addition, this is where they think humans migrated from. First in small numbers, and then the numbers grew and they can actually be traced as they migrate through the continents. Most of the migrations are traced through fossil remains. Fossils are found in sedimentary rock. Other forms of rock are too hard, and the formation of sedimentary rocks allows for other things to be incorporated. The glaciers pushing down through New England and through the Midwest pushed the plant life down further in the continent. So just beneath the glaciers was a band of tundra, and then there were grasslands. In the extensive grasslands, not only did the large animals thrive, but there was also an explosion of species in songbirds and snakes and frogs, smaller animals that feed off of the seeds and off of these smaller plants. So you can see that throughout geologic history, changes in climate have really affected the species that live here and where and how they've lived.
We've demonstrated the importance of the Earth's tilt in its orbital path around the Sun in creating seasons. Much of our understanding of planetary motion has come from mathematical calculations. But what evidence do we have of the tilt and orbit of the Earth? Evidence that the Earth's axis is tilted, which causes warmer summers and colder winters, comes from observing the position of the Sun in the sky. The Sun is always higher in the sky at midday than at other times of the day. In the morning, the temperature is usually cooler, but as the Sun gets higher, the temperature rises. Later in the afternoon, as the Sun gets lower in the sky, it gets cooler. However, in the winter, the Sun's path is not as high in the sky as it is in the summer. To learn about the Sun's path, we can look at the shadows that an object casts when the Sun shines on it.
Okay, 12. Everybody, where's the Sun? Let's look. 12, put your arm up there. Angle it. Angle your arm and bring it this way, right where your stick is.
Amanda, I can't
Right. So over here we know that this line right here is 127. When we come out at 2:30, which direction do you think that you'll mark? Do you think you'll go this way or do you think you'll go this way?
Down.
You think you're going to be coming this way?
Yeah.
That's your prediction?
Yes.
Okay, so at 2:30 we'll see exactly where we are.
The Earth moved and the sun used to be there.
Yep.
And then it reflected to here and it moved like about an inch. the sun never moved, but the earth rotates, and so it seems like the sun moves. Yeah, because it's pointing in the shadow moved.
The shadow moved
And it shrunk.
and it shrunk. Okay, and why do you think that happened? Because the sun moved?
The sun is still there, I think. Well, a little bit to the right.
Yep.
And the shadow, it's moved from 1250 and got right.
What would you like to say?
I think that the Earth was rotating a little, and that way it was going a little far further away from the sun.
So you think the Earth is rotating and going further away from the sun?
Yeah.
Before each observation, the children predicted the length of the shadow they would see. They noticed that the length of the shadow changed during the course of the day. Now let's join a group of workshop participants as they track the shadows over the course of a day.
Well, if that's roughly 11, then that would be roughly 1. It would be about the same length, but pointing in a different direction.
All right.
All right?
It's like a half an hour, so it would be in shorter for sure.
45 minutes. So let's say 10 to 3, 9. And then we're supposed to estimate where we're going to
Okay.
right?
Because that may not be due east. We need a compass. Okay.
So this is 11.
Well, but if I lean this way, I'm going to be
I think my new one's going to be here.
Did you lean at all? Well, I mean, if I stand on this road right here.
If the sun rises in the east and sets in the west,
And how do you know that?
where do you think east is?
The participants also observed the movement of shadows and, like the children, saw the changes in length.
Oh, they want to get shot.
Oh, let me write this.
Hours 12.
Getting shorter and shorter. And your dress is ending up. Check out our. I know. Perfect.
This is the one I did at 12:05. 10:50, 11:30, 12:05.
Okay,
so now it's
110.
I've 109.
Okay. I'm just doing
So
your
it's
head.
it's gone quite a bit in an hour and 5 minutes.
You said 109?
Yes, that's what I have. 109.
Wow, that's really different.
Look at. If I would have stuck with my original predictions, I was out more. Then I started coming in, but now it's going out. Isn't that weird? I would never have thought it went over there, to go over there. 2 o'clock. Want to put an X for me?
supposed to be doing that same fan thing.
It's doing what?
Like a fan thing like that.
Fan? Like this
Well,
one?
yeah, see, because it was curving inward. And
Right,
now
look at it. It's going
outward.
out. If you trace this, it's going this way. You're right. It's doing a curve. It's not only getting smaller, the shadow, it's moving.
From shadow evidence, we cannot tell whether the Earth is turning or the sun is moving across the sky.
We can see in this demonstration how the tilt of the Earth's axis affects the number of daylight hours for people at different latitudes. We've placed 3 observers on the globe, one in the northern hemisphere, one at the equator, and one in the southern hemisphere. All 3 are at the same longitude. Now let's see what happens for each observer on the vernal or autumnal equinoxes. All 3 of our observers see sunrise at the same time, have the same number of daylight hours, and later see sunset at the same time. Now let's move to the position in the Earth's orbit around the Sun when the Earth's axis is tilted toward the Sun, the orientation of the Earth on the summer solstice in the northern hemisphere. Now let's see when each observer sees sunrise and sunset. They do not all see the sun rise at the same time. And they do not all see the sun set at the same time. The number of daylight hours are longer for the observer in the northern hemisphere and shorter for the one in the south. Now let's move to the position in the Earth's orbit around the Sun when the Earth's axis is tilted away from the Sun, winter solstice in the northern hemisphere. Let's look again at when each observer sees sunrise and sunset. Again, they do not all see the sun rise at the same time. And they do not see the sun set at the same time. The number of daylight hours is shortest for the observer located north of the equator. Here we've plotted the sunrise and sunset times for Boston, Massachusetts during the year. You can see how the hours of daylight changed. We have over 15 hours of daylight each day in June, but only about 9 hours of daylight in December. The tilt of the Earth's axis causes the number of daylight hours to change during the year. In the winter, you may be getting up when it's dark, while in the summer, the sun and the birds may be waking you up earlier than you like. At the end of the day in the summer, you may be eating dinner by daylight, while in the winter, you'll need artificial light. In the northern hemisphere in summer, we have longer, hotter days because of the tilt of the Earth's axis. By measuring shadow lengths at different times of the year, we can see how shadow patterns change with the seasons. These changes occur because the path of the sun in the sky changes with the season. In the northern hemisphere, the sun is only directly overhead at the Tropic of Cancer, 23.5 degrees latitude north of the equator, on one day of the year, usually about June 21st, the summer solstice, or the longest day of the year. North of the Tropic of Cancer, the sun is never directly overhead, not even in summer. Therefore, a shadow will always be seen at midday. As the Earth moves in its orbit, on about September 23rd, the sun is directly over the equator. This is the autumnal equinox. At this time, the length of the day and night are equal. On around December 21st, the shortest day of the year in the northern hemisphere, the sun is directly over the Tropic of Capricorn, 23.5 degrees south of the equator. And on about March 21st, the vernal equinox, the sun is again directly over the equator, and again the length of the day and night are equal.
The sun provides a constant amount of light energy to the Earth, but as a result of the uneven distribution of the light over the Earth's surface, there are regions which are extremely harsh. In the northern hemisphere, within the Arctic Circle, the sun does not rise on the winter solstice, while in the Antarctic, it does not set on this date. In fact, at the North Pole, the sun is not seen for days on end, while at the South Pole, there is continuous daylight. In this demonstration, we have a ball in a box tilted on its axis. We stuck 3 pins in this globe, one at the Arctic Circle, one in the United States, and one on the equator. The globe is oriented so that the North Pole is tilted away from the light bulb, simulating the sun. The globe is slowly rotated. The pin on the Arctic Circle is always in the dark when the North Pole is tilted away from the sun. The North Polar region has 24 hours of darkness.
So while there are dramatic seasonal changes occurring away from the equator, there are also seasonal changes in between the tropics of Cancer and Capricorn. From latitudes 23.5 degrees north and south of the equator, the variations in the length of day and the amount of sunlight are much less than at higher latitudes. In most parts of the northern and southern hemispheres, there are 4 seasons. But in the tropics, there are 2 seasons, a rainy season and a dry season. We'll explore the climate and weather conditions that influence seasons in more detail in our next workshop, Wind and Weather.
In this workshop, we've looked at the reason for the seasons, and clearly the Earth's distance from the sun is not the reason. However, this is one of the most common ideas that children hold. Children also sometimes think that it is hotter at the Earth's equator because the equator is closer to the sun. However, the Earth is so far from the sun that any difference in the distance from the sun to the equator or from the sun to the poles is truly minuscule. For instance, on this model, the equator is 5 centimeters closer to the sun than the poles are. But on this scale, the sun will be about 1 kilometer away. So the fact that the equator is slightly closer to the sun is insignificant. The equator isn't warmer because it's closer to the sun than the poles. The equator is warmer because the light is more intense at the equator. Today we've talked about how the tilt of the Earth's axis causes changes in the length of the day and the seasons. But the climatic conditions in each season are not just the result of the tilt of the Earth's axis.
Next time we'll explore these climatic conditions as we look at how light energy influences weather patterns here on our Earth.
So goodbye until then.
Remember to check out our website for additional information, activities, and discussions with your colleagues. The address is www.learner.org/channel/workshops/shedding-light. And if you don't have access to the web, you can share your thoughts with us by email, fax, or mail. Our email address is channel@learner.org. Our fax number is 617-496-7670, and the mailing address is the Annenberg CPB Channel, Smithsonian Astrophysical Observatory, 60 Garden Street, MS-82, Cambridge, Massachusetts, 02138.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.